Okay, good morning. Welcome back. We're definitely getting to the end of the semester. So let's see where we are, where we've gotten to. So we have what we did last time was we completed our discussion of what are called Maxwell's equations, which describe all possible configurations of electric and magnetic fields in space. And some of these are more familiar than others. Gauss's law relates the electric flux, the component of E perpendicular to a surface or parallel to the normal to a surface, times the surface area on some enclosed surface, a surface that encloses some space, to the amount of charge inside the space. And Gauss's law for magnetism does the same thing with magnetic flux, but since there aren't any magnetic monopoles, as far as we know, no north poles without south poles or south poles without north poles, then the sum of that flux, magnetic flux, has to be zero. Now, as we talked about last time, that doesn't mean that the magnetic flux at any particular location over any part of a surface is zero. It just means that the sum, when you add it up over the whole surface, has to be zero. And we saw that same thing with Gauss's law. Remember that we saw that a charge outside our closed box did make electric flux that was negative or positive at various places on a closed surface, but that flux added up to zero. And so the amount of charge inside had to be zero. Faraday's law gave us some surprising physics. It said that we could have a curly pattern of electric field, or a pattern of electric field such that the integral of E dot dl around a round trip path would be not zero. That was essentially due to a changing magnetic field, or the way we write it in this equation is a changing quantitatively, is a changing time-varying magnetic flux. So we have to take into account. And in this case, we're talking about a path that's some closed path, goes around and comes back, and the flux is on this surface inside the path, surface bounded by the path. And a more compact way of writing it is that the EMF, the absolute, not worrying about directions, which we can find with the right-hand rule, that the EMF, which is indeed this integral of E dot dl on a round-trip path, and if it's an E made by charges, that's going to be zero, but if it's an E made by time-varying magnetic fields, it won't, is equal to the time rate of change of the magnetic flux. And finally, the Ampere-Maxwell law, the integral of B dot dl around a round-trip path, was proportional to not only to the current inside, but also to the time rate of change of the electric flux over the surface bounded by that path. And a more compact way of writing it is this green. We don't have a name for B dot dl. It's not EMF or anything like that, but we can write it proportional to the current inside and the time rate of change of the electric flux on that surface. And what was this? What good was this? Well, we used Maxwell's equations to show that under certain conditions, a time-varying magnetic field could actually create a time-varying electric field, which creates a time-varying magnetic field. They're sort of sustaining each other without needing any charges nearby at all. And we found that this was true if and only if the region of space where these fields were non-zero propagates means travels through space in some direction with a speed equal to the speed of light. And for this to work out, the direction of propagation, so we have here v hat, was the direction of E cross B. And note that these are just unit vectors, so these are just directions. That relationship is not true for V, E, and B, the full vectors. Now, what we didn't figure out last time is how that got started. And so what happened when this, how do we get this going? We see that once it's going, it can sustain itself, but the question of how this is produced is fairly mysterious. And this region of space where we have a time-varying fields that's propagating through space. What we talked about last time, this was a very simple example, just a simple pulse, where if you sit in space, you'll see nothing, and then you see an electric field up and a magnetic field out. And if we pause this just for a minute, we can see that the electric and magnetic fields are at right angles to each other in such a way that if we take the cross product of E cross B, so we point our fingers up in the direction of E, and then we fold them toward ourselves in the direction of B, our thumb sticks out in the plus X direction, and that's the direction of propagation of the wave. Okay, so the question is, how can something like this get started? And you might guess, since we've talked about the effect, what the way of making fields, so stationary charges can make electric fields, moving charges make electric and magnetic fields. In this particular pulse, this is our simplest pulse. So the question is, are the electric and magnetic fields constant in magnitude across this pulse? And in our very simplest case here, this particular case that we're talking about and the one we talked about last time, the answer is yes. That is not necessarily true, however, and we will see later today that you can have sinusoidally oscillating electric and magnetic fields or various other kinds of changes in magnitude here, and we'll talk about that. So what we haven't talked about is what happens when a charge is accelerated. And in order to talk about that, we need a representation that we haven't really used because it is really not very useful for most things. But it's useful to us now in talking about this situation. Where are we? Here. So we're going to talk briefly about electric field lines. Now, you may have seen electric field lines in some other course, and you note that we haven't used them. They're not really very useful for the kinds of problems that we're trying to solve, but in this particular case, they really help illustrate a point. So what's an electric field line? Well, it's a very simple construct. Suppose that we have a positive charge here, like the one we see in this Python program, and we want to measure the electric field at a bunch of different locations all around the charge. Now, this is an odd representation though, because we're using vectors, okay? So the tail of the arrow is at the location where we're measuring the field, but the length of the arrows are all the same. So we're not showing the magnitudes here. This is only the direction of the electric field, and we're not showing representing the magnitudes at all. So we have these unit vectors in the direction of the electric field around this charge measured at various locations. Well, to make field lines, all we do is we just connect the vectors. Okay, so that's a field line, and it just shows. Now, there's a lot of information that's lost when you have a field line. You've not only lost magnitude information, although there's some information on how close the lines are together, but you've lost direction. So we just need to know that this is a positive charge, and so the field's pointing away. But that's basically what a field line is. You're just connecting all these unit vectors that show the direction of E at a whole bunch of locations, but not the magnitude. So that's all there is to field lines. However, some interesting things happen. So here's our charge. And what we're going to do with this charged particle here, it's a positive charge, it's a proton, and here are the field lines representing the electric field due to this positive charge, okay? And what we're going to do is we're just going to give this charge a little bit of a kick, okay? So it's going to be very, very briefly accelerated. Remember, acceleration is dv dt, so we're going to speed it up from 0 to some constant speed by just giving it a little bit of a brief kick downward, so just a tiny kick. Now, it can be a pretty big kick, but okay, so what's going to happen is the charge is going to accelerate briefly and then coast downward. Let's see what that does to the electric field. Okay, what the heck was that? So the red dot here, this top red dot is the original location of the charge. And this dot that you can't see is where the charge currently is now. And then you saw that it coasted downward, okay? Let's try this again and pause. We'll just stop this animation when we're, okay, so we've just stopped. So what's happened is the charge started out at this top location, we gave it a kick, and it coasted downward. Well, these field lines look odd, so let's think about what's happening. So if you're an observer standing, say, here where my cursor is, what you see is unambiguous. You see an electric field pointing away from the current location of the charge. And you don't necessarily have any idea that the charge used to be at that top location. However, if you're an observer a little farther out, so you're an observer here, say, there hasn't been time for information to get to you that the charge has moved, because information travels at the speed of light and you're too far away for that information to have gotten to you yet. So if you're 2 feet away, then it takes 2 nanoseconds for that information to get to you, and it's only been a nanosecond and a half, so you don't know yet that that charge has moved. So what you detect with your proton on a spring is an electric field that's actually still pointing at the original location of the charge. And so I'll put my cursor here where you're standing, and we'll start it running again. And now all of a sudden you see that the electric field is pointing toward the current location of the charge and not its original location. Well, what do you detect at that instant in between seeing the electric field just pointing away from the original location of the charge and pointing toward the current location of the charge? What you see here, so I stopped it right here. What you now see is an electric field pointing in an odd direction. It's actually pointing up. It's connecting this field. The field line is an interesting representation because it's connecting the line of the field pointing toward the current location of the charge with this old line, this field that was pointing toward the previous location. And just at the second this information gets to you, you actually see a perpendicular field. And that field is called the radiative electric field. It's that little pulse of field that's called the radiative electric field. And you only see it at that moment when that information gets to you. Okay, so what does this actually look like in a more familiar representation to us? So here's a charge. It's currently a positive charge. And we're going to give it a kick and accelerate it downwards just like we did before. And what we're going to draw here is we're going to draw only the fields in this little pulse. Okay, we're not going to draw the electric field that you would detect now that's pointing away from this charge before it starts moving. And we're not going to draw the electric field that's pointing away from this ordinary electric field, the 1 over r squared electric field that you all know very well. It's pointing away from it. We're only going to draw this pulse of radiation. And so what happens is we get this pulse of radiation, and with electric fields perpendicular to the direction the radiation is moving in, spreading out. And so we get these electric and magnetic fields spreading out all over. Let's do it again, except in certain directions. So this time look and see where we get a magnitude of the fields are. Okay, so the magnitude of E is large here, small here, and it looks like it's actually 0 right along the direction along which the charge was accelerated. And what happens if this is a negative charge? Because actually accelerating electrons is a lot easier than accelerating much more massive protons. So if it's a negative charge, we get the same pattern, but the fields point in the opposite directions. Not a big surprise. And what we see is from this brief acceleration, you just saw this brief pulse of radiation. Okay, so this charge is only producing these radiative fields during the time it's being accelerated. Okay, so that's kind of a lot of visual information. So let's actually try a 2D slice through it. This one. Okay, so what we're doing is just taking a 2D slice in the plane of the screen. Okay, so we're only gonna show that. So here's our positive charge that's going to be accelerated in the direction of this yellow arrow A. All these green arrows are R vectors. They're pointing to our observation locations. And what we see at these observation locations is interesting. So at this observation location, we see an electric field pointing up, a magnetic field pointing actually into the screen in the -z direction. And this little magenta arrow is the direction of propagation, the direction the pulse is traveling. And along this particular, it's just really the direction of the R vector, the observation, okay? And we see that the magnitude of E, and therefore the magnitude of B, since they're related, is greatest along a line perpendicular to the acceleration. Okay, and along this line of the acceleration, the electric and magnetic fields are different. No, so it's not the pulse that's accelerating the charge. We accelerated this charge by taking a sledgehammer and hitting it. Okay, that's probably not a really good way to accelerate a charge. But suppose we brought another positive charge really close to our charge of interest, okay? So here's our charge of interest, and we just bring a positive charge really close to it briefly and accelerate it. Or we take a dipole. We have a dipole here that briefly, say here, that exerts a force on this positive charge, and then the dipole collapses and annihilates each other. And okay, so we have lots of ways to accelerate charges. This pulse is a result of the acceleration of the charge. It's not a cause of the acceleration of the charge. Does that make sense? So what we need to do is we need a mathematical equation that describes the magnitude and direction of the electric field, and therefore we can derive the magnetic field from that in one of these pulses of acceleration. Okay, so we need an equation that describes this. It has to give us the magnitude and the direction as a function of distance from the location where the acceleration was applied. And we note that there seems to be absolutely no radiation along the line of the acceleration. The magnitude is 0 here, and the magnitude is highest along a line perpendicular to the acceleration. So this equation needs to capture those things. So let's see if we can, what that equation might look like. So we're going to write an equation for the electric field in a pulse of radiation. So we're going to call it the radiative electric field to show that it's not just the Coulomb field you get from a stationary charge. And it looks like this. So we've got a proportionality constant, and you won't be surprised to know that's a 1 over 4 pi epsilon 0. It's proportional to the charge. So we've got a Q here. The distance dependence is interesting. The distance dependence is actually only 1 over R. So it falls off, the magnitude of E falls off much more slowly than the 1 over R squared field just from the stationary charge. There's a C squared here, and that distance dependence has real practical consequences. On a clear night, when you look up in the sky and you see stars, what you see is, of course, light emitted from these stars. Most of those stars are really far away. But this electromagnetic radiation radiated by accelerated charges in the very hot stellar atmosphere only falls off like 1 over r, so it travels very, 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 very long distances to get to your eye. So we have a c squared r, and then we have some funny things. We have a minus, okay, we know about minus signs. And there's an a perpendicular, where a is the acceleration. So a is dv dt, but what on earth is, we know what everything else is. We know what c is, we know what r is, you know what q and 1 over 4 pi epsilon 0. So what is this a perpendicular? Well, a perpendicular is the component of the acceleration that's perpendicular to r. So remember that when we had a positive charge that was accelerated downward, and we had an observation location here, we got a big electric field, and that it corresponds to this angle. This is, so A being completely perpendicular to R. But if we picked a different observation location, so here's our positive charge, it is accelerated downward, but we're going to pick our observation location here. Well, the acceleration is not perpendicular to r, but we can write the acceleration, we can express this acceleration as the sum of two vectors. So this would be a vector perpendicular to r, and that would be a vector parallel to r. And so this would be perpendicular to r, and we would call this a parallel, but we're not actually very interested in it. And it's that component of a that's perpendicular to r, that's the a perpendicular in our equation up here. Or another way to draw this, we get the same result. So here's R, here's A, and we sometimes just draw a perpendicular that way. It's exactly the same vector. So here A is perpendicular to R, but here it's not. Okay, so how are we gonna find a perpendicular? Well, if we know this angle, theta, then the magnitude of a perpendicular is equal to the magnitude of the total acceleration times the sine of theta. Okay, so that's what a perpendicular is. And now what does this minus sign mean? Well, we go back to the drawing on the left here. Let's see what this would tell us. The acceleration, so here we are, this situation here where A is perpendicular to R. This says that this is a vector equation, so we know the magnitude of the radiative field, but what about the direction? Well, it says So the direction of E radiative has to be equal to the direction of this vector piece of the equation on the other side. And what we have, the only thing that's a vector on the right-hand side is this A perpendicular. So if E was just proportional A perpendicular, it would be in the same direction as A perpendicular. But actually, there's this minus sign. So in fact, the electric field at the observation location is going to be opposite to A perpendicular here. That's for positive charge. We note that we've got the same problem we always do. If this is a negative number, if Q is a negative number, then it's going to have an additional negative sign and they'll cancel out, and then the E will be in the direction of A perpendicular. So let's see what we get at these cases over here from this equation. So at this observation location, A perpendicular is that way, and it was a positive charge, so therefore the electric field, the radiative electric field at the observation location when the pulse passes us is going to be in that direction. And maybe you can see now that that is what we were seeing in that VPython program here. So here we've got this charge that's accelerated down. At this observation location over here on the right, we've got, so we've got E up, we've got B out of the page, but it's, and the direction of E, the orange arrow is always E. The direction of E is in fact opposite to the direction of A perpendicular. Down here, we've got E, so the perpendicular component of A perpendicular to this R is going to be along that direction. So we have E that direction, B in an appropriate direction to get the direction of propagation correct. Here we, again, E is perpendicular to R, so it's the component of, and it's smaller in magnitude because the perpendicular component of the acceleration is smaller. And then when we get down to here at the bottom, there is no, the component of A perpendicular to R is 0, so the magnitude of E is actually 0 here. And it works on the other side also. So here we get E. Now here the magnetic field is into the page because the direction of propagation is to the left instead of the right. So direction of propagation depends on your observation location, okay? It means it's basically the direction of R, the vector from the source to the observation location. So that's the direction of propagation. Okay, so let's see if we can practice this a little bit. So we have a proton here that's accelerated basically toward location S. And the first question is just, what is the direction of propagation of radiation that reaches location P? So we're just asking about the direction of propagation here. Make sure you're answering the question that's asked and not some other question. So the correct answer is indeed 1. That is the direction of propagation. And what does that mean? Well, let's remind ourselves what all these terms mean. It just means what way is the radiation traveling? And that's in the direction of, so here's the vector R that goes from the source to the observation location. And so any radiation that reaches location P must have been traveling straight up. So in fact, the direction of propagation is indeed straight up. That's all there is to it, and it would be different if you were at location S. Okay. So now we know that. Let's ask a different question. So same situation, same observation location. But now the question is, your observation location is location P. If you're standing at location P, to you, what is the direction of A perpendicular? Drawing a diagram really helps. Okay, so the predominant answer is 3, which is indeed correct. So let's see how to figure this out. So we have, since the perpendicular means perpendicular to the direction of propagation, we want to draw the r vector. And then we need to draw a line that's perpendicular to r. So that's the line that's perpendicular to r. Now, what's the component of acceleration that's perpendicular to r? Well, that's going to be the component that's parallel to r, and that's going to be the component perpendicular to r. Sorry, got it backwards. That's the vertical line is the component parallel to r. So this horizontal arrow is the component that's perpendicular to r. So the component of acceleration that's perpendicular to r is A perpendicular. Remember, we can draw it like that too. Okay, so you know what the next question is going to be, right? You know the direction of r, you know the direction of A perpendicular. What's the direction of the radiative electric field that you observe at location P? Okay, so mostly you're absolutely in the right space. So that is indeed the correct answer. 7 is the correct answer. Let's see why. We had R, we had a line perpendicular to R. We found A perpendicular. And remember that our equation, 1 over 4 pi epsilon 0 minus q over c squared r times A perpendicular, says that for a positive charge, where this is a positive scalar, the direction of the radiative electric field will be opposite to A perpendicular. So in fact, at location P, we're going to see a radiative electric field pointing that way. So how would we get the direction of the magnetic field in that pulse? If you were at P and you had not only an electric field detector, but a magnetic field detector, what would be the direction of the magnetic field you detect in that pulse of radiation? Well, the direction of propagation is going to be the direction of E cross B, right? So here's our direction of propagation. So in a cross product, we want our thumb ending up pointing up, and our fingers start out pointing in the direction of the electric field. So therefore, we are going to have to fold our fingers out of the page in the plus Z direction in order to make that work. So therefore, B radiative is going to be out of the page by the right-hand rule. Yep, you're right. Okay, one last question. Okay, since this all depends on your observation location, now let's consider observation location S. So at observation location S, what is the direction of A perpendicular? So the majority are indeed correct. The magnitude of A perpendicular is actually 0 in this situation. Those of you who said 4 identified the perpendicular direction, but then you didn't think about what the magnitude of a vector that you'd have, along that direction that could add to A would be, okay? So this is definitely our R vector, and so that is indeed the direction of something perpendicular. But in fact, there is no component of A perpendicular. The only component of A is actually parallel to R. So in fact, that's one of the places where we would find that the electric field was 0 because it's along the direction of acceleration. So quickly, let's actually just calculate a magnitude. Let's calculate the magnitude of a radiative electric field, okay? So let's consider a situation where we've got a negative charge that's accelerated that way. And we've got an observation location over here. And we know that the magnitude of this acceleration is 2 times 10 to the 17th meters per second per second. Now that's a big acceleration, but it's for a tiny time. So this thing does not get going faster than the speed of light, or even necessarily close to it. And the magnitude of R, so the distance to the observation location, is 2 centimeters. And let's find the radiative electric field here. We know that this angle here is 20 degrees. So theta equals 20 degrees. Okay, so the first thing we have to do, and here's our equation, E radiative is 1 over 4 pi epsilon 0 minus Q A perpendicular over C squared R. And we just want magnitudes here. So find the magnitude of E radiative. So the first thing we have to do is find A perpendicular. So here's our line perpendicular to R. And so the component of A perpendicular to R is going to look like that. Or we can draw it that way. And so the magnitude of A perpendicular is just equal to the magnitude of A times the sine of 20 degrees, which is 2 times 10 to the 17th meters per second squared times sine of 20 degrees. And it's 6.8 times 10 to the 16th meters per second squared. So less than the full, smaller than the full acceleration. So the magnitude of the radiative field is just going to be, we'll use our equation here. So it's 9 times 10 to the 9 Newton meters squared per Coulomb squared. Oh, this is an electron. We do need the charge, so it's an electron. So the charge of an electron is going to be minus 1.6 times 10 to the minus 19th coulombs, but we're just looking at magnitudes here, so we'll take an absolute value of 1.6 times 10 to the minus 19 coulombs. times the magnitude of A perpendicular, which is 6.8 times 10 to the 16 meters per second squared. And that's divided by the speed of light squared, 3 times 10 to the 8th meters per second squared, times the magnitude of R, which is 0.02 meters. And we get a magnitude of 5.47 times 10 to the negative 8 newtons per coulomb, if I did the arithmetic right. Now, just for comparison, we could calculate the coulomb, the other piece of the electric field, just this coulomb field coming out from the charge. And we could get, so if we do that, just the 1 over 4 pi epsilon 0 q over r squared. And if we do that, we get, you can calculate it, we're going to get about 3.6 times 10 to the minus 6 newtons per coulomb. So at this point, it's bigger. But this field falls off much faster. The 1 over r squared falls off much faster than the 1 over r field. So by the time you get to 200 meters, then the radiative electric field is actually bigger than the what we're calling the Coulomb field, and it's going to stay that way. Okay, so questions about that? So let's think what would happen if, instead of just giving a charge a kick, we actually had a charge on a spring that could oscillate up and down. So suppose we had an electron on a spring, and so it oscillated up and down. Well, and that's not as crazy as it sounds, because the bond between the electrostatic bond between the electron and a nucleus in an atom is indeed rather spring-like. So you could actually make this atom into, think about a hydrogen atom because it's simplest, you could make it into an oscillating dipole where the electron's vibrating. At that point, the electron is accelerating. So we'd get, so sinusoidal motion. So we'd get the y position is its maximum position times sine of some frequency omega times t, which depends on the stiffness of that bond, right? So the velocity in the y direction would be dy dt, and so we'd get an omega y max cosine omega t. And the acceleration is just dvy dt. So we'd actually get a sinusoidal acceleration. We'd get a minus omega squared y max sine of omega t. And so it would look something, and so the acceleration is sinusoidal, so the radiation itself would be sinusoidal too. And in fact, so we get an E radiative sub y. Let's not worry about signs for a minute, since it's oscillating, I mean, direction, since it's going to be up and down. It would be a 1 over 4 pi epsilon 0 q over c squared r omega squared y max sine of omega t. So we get some sort of sinusoidally oscillating electric field if we, so if we plot E sub y, we'd get something that looked like that. which is a really terrible drawing of a sine wave. And of course we'd have a magnetic field too. So what we'd get would be something that looks kind of like this. So if you stood somewhere and you got out your electric and magnetic field detectors. So let's say we're standing at this location, and the field we're measuring, the electric field we're measuring here at this location is shown by the red vector, and the magnetic field is shown by the black vector. So if you're just standing in one place, what you see is that the amplitude and direction, the magnitude and direction vary with time. Let me rerun this. Now there's some terms for sinusoidal waves. There's a thing called the wavelength. And so the green marker at the bottom indicates one wavelength. What's the wavelength? Well, it's the distance spatially now, so you need two observers, or you need to walk around to measure this, between one peak and the next peak, or one trough and the next trough, whatever you call it. So that's called the wavelength of the radiation. And the amplitude of the radiation is just the maximum value this thing has. So right now our red arrow looks like it's showing us the amplitude of the radiation. That's the maximum value that E ever has. And of course, there's a amplitude for, there's a wave in the magnetic field is oscillating in the XZ plane here too. So that's basically what we get. And what we could also, and so what we're going to see here, if we have this, so here's a little antenna, okay? This is just a little piece of a metal bar that's connected to a power supply. And suppose our power supply provides a sinusoidally oscillating potential difference to drive a current in this antenna. So electrons, the mobile electron C moves up and then down and then up and then down, and it's accelerating all the time, right? So if we look at the radiation made by these electrons, which are oscillating along the y-axis, and we're only going to look in one plane because it's sort of impossible to make any sense of it if we look at other planes too. So in the XZ plane, we'd see radiation coming off something like this. And notice that it's really big close to the source, but then it dies off fast, and then it doesn't seem to decrease very much in amplitude. That 1/r decrease actually is kind of a slow decrease in amplitude. And now, of course, there are magnetic fields too, and so if we draw both of them, we're going to see patterns that look like this. It's pretty, isn't it? They're kind of, these patterns are cool. Okay, if we graph, so this is a graph of electric field versus time at one location. So E sub y versus t at one location. And so since this is a time graph, there's another term here. This is this time interval here from this time interval t is called the period, the time between one peak and the next peak if you just sit at a given location. If you plot versus E sub y versus x, so this is a spatial plot now. So we get this sinusoidally varying, and this distance between the peaks here, this is called the wavelength. And it has a symbol lowercase Greek lambda. And the symbol for period is just an uppercase T. And this distance here is called the amplitude of the wave. And there's some relationships here. So we know, of course, that the angular frequency is 2 pi over the period. There's a thing called the frequency. So this is in radians per second. The frequency is just cycles per second. And that's, it's 1 over t, which is obviously omega over 2 pi. And frequency, so now the symbol for amplitude, well, there isn't, I don't think there really is one. I mean, in many equations, it's actually just written as a capital A. But if we look up here at our equation for the radiative electric field, we see that the amplitude is everything, is the maximum. The amplitude is kind of is this whole thing, really. So it's just whatever is multiplying. So the amplitude of the acceleration of the electron was just the maximum distance it was displaced. Sometimes people use just a capital A, they don't want to write everything out. So 1 hertz is 1 cycle per second. Now, we've actually seen an antenna at work, because remember our demo with the machine that had the little tube attached to it. So the thing the transmitter that looked like this, and it had a metal bar sticking out in front here. Well, that metal bar is an antenna. And what this power supply is doing was driving a current sinusoidally, and then that way. So sloshing electrons this way and that way and this way and that way, back and forth through the antenna. And so we have the electrons in that antenna being accelerated sinusoidally, and they are producing electromagnetic radiation. So what we're going to get is electromagnetic radiation coming off from that antenna, just like in that VPython program we saw. And the strongest radiation is coming off perpendicular to the direction of acceleration. So maybe I should write A's here for how we're accelerating electrons. So if we drive a sinusoidal current in this antenna, we're going to get electromagnetic radiation coming out with an electric field that is going to be, well, it's actually going to be, because there are electrons accelerating, it's going to be in the same direction as a perpendicular. So we're going to get electric field going this way and that way. And so what happens if we have a piece of wire here with a light bulb in it? Well, here comes this radiation with electric fields oscillating this way and that way. And it gets to our piece of wire, and what it can do is it can drive electrons in the light bulb, in the wire in the light bulb. So we can get, I'm going to write a little I for electron current, electron current. So not only do we get, so our radiation can accelerate electrons in the light bulb, in the wire, drives a current through the bulb, and so the bulb can actually light. It is indeed an AC current. AC just stands for alternating current. So it's an AC current. And why don't we see the light bulb flicker? Well, we don't see the light bulb flicker because the frequency of the oscillations is too fast. And so the light bulb never has time to cool down. The filament never actually has time to cool down. It stays hot even when the current momentarily stops. So the light bulb stays hot, you get in, it looks like a constant glow, even though the current is indeed sloshing back and forth through our light bulb. So we see that this radiation from accelerated electrons can actually affect other charges. So we get to a point where we're accelerating charges in this wire, or we're making the move anyway, and that lights the light bulb. Now you can actually take it a step further. We have accelerated electrons in our wire here because they're oscillating sinusoidally, so they can radiate too. So we're going to get a little radiation from these electrons in the wire. Now we're losing energy here though a lot because, of course, the electrons in this electrons in this antenna radiate in many directions. Now you remember that if we put our light bulb detector thing over here, nothing happened, no light. And that's because it was lined up with the direction of acceleration of the electrons, and therefore the radiative electric field was 0. But any place we put it kind of around this antenna, we did get it to light. And that means that energy is being radiated off in lots of directions. And when we get here again, we're going to accelerate these electrons. They also radiate off some energy in more directions, but the amount of energy radiated decreases a lot as we go through multiple cycles of that. So we do have, so this afternoon in recitation, we'll practice with radiative electric fields, radiation. On Tuesday of next week, which is getting near the end, so what I'd like to do is talk a little more about light. And in particular, we have 2 models of light that we need to think about. We have this light as an electromagnetic wave, and we have light as photons. And how are these things even related to each other? Which one is right? How do we think about that? And also, what happens when light goes through something that's not a medium, that's not a vacuum? And then on Thursday, we're going to talk about sparks, which is sparks in air, which is kind of a review of pretty much everything we've done in the semester. So that's the agenda. Okay, so what was important in today's class?
Dr. Chabay?
Yeah.
I had a question about, well, I'm not sure if this is part of what you were meaning we were going to address like next class or the class after that, but I was just wondering that how does the superposition principle of like fields, does that only apply to fields that are being created by a charge?
No, it applies to everything. And it applies to radiative fields as well. And that's a pretty perceptive question. So the net field at any location in space is the sum of all the fields due to all sources, including stationary charges and accelerated charges. So, so in this diagram here, you know, if we looked at some location, say here, we'd have a radiative field due to this antenna, maybe here, but we actually would have a little tiny bit of a contribution from the electrons oscillating in this wire here. And so the net field would actually be, well, probably a whole lot more like that or something. So fields are fields. I mean, the only way you know what's made a field is if you discover, like, you have a lot of ways to measure and you discover that it's falling off like 1/distance squared, or you see that it's oscillating or something. But at any instant, in any location in space, the net field is the net field due to whatever we got.
Right. I guess what I was wondering was that since light is just the combination of two, a magnetic field and electric field, how do we think, like, how do we sometimes like say things like this absorbs light, or like this light is absorbed by this particle or something? Why does the light get stopped, or why do those fields get, like, how do they get absorbed by a particle and I guess stop going forward?
Okay, so that's a really good question. And so we actually have two different models, and the absorption and emission model, the sort of quantum model, says energy is absorbed and a different photon would be emitted or whatever. In this classical model, and we actually need both of these models. There is a synthesis of these two models. In this classical model, and you actually are completely on the right track. So in this classical model, what happens, say, is suppose we have, a piece of cardboard, say. And suppose we have some light coming this way. So we have light. So we have electric fields, and we have magnetic fields, heading toward this cardboard. Well, this light just goes right through. Okay, so fields penetrate matter. So we have, this is light 1. But we are accelerating, we're accelerating electrons in the cardboard, and there are a lot of them. So and those electrons, accelerated electrons, also radiate, and we call that re-radiation. So we get some radiation coming out of the cardboard as well from the electrons in the cardboard. And so the net field over here, where your eye is the sum of those two, and the incident radiation and the radiation, re-radiation from all the electrons in the cardboard. Now, it actually just depends on the structure of the material, how that's going to play out. So if this material is cardboard, in fact, these two things add up in such a way that you get 0 on the other side. Okay, so it means that the peaks of one and the troughs of the other come out simultaneously. If it's something like glass, you're still getting all those electrons accelerated. They're still re-radiating, but they re-radiate in such a way that when you add them all up, you get non-zero fields.
Okay, so the fields don't stop. It's just as they go through the material, another field gets created, and based off the combination of those two. Okay, that's really interesting. Do we have a way of, like, is there any way for us to know how many different, I can't imagine there is, but how many different, like, sources go into a single, like, net field? Like, is there a way for us to detect where, like, what fields make up a 0 net field, or just be?
I don't think so. No, I mean, we can predict it on theoretical grounds, and in fact, there's a lot of math that goes into doing this. It's pretty well worked out for X-ray studies of crystals and things like that. But no, I mean, so you'd have to say, well, I have to model my cardboard as a collection of, let me take a tiny piece and say we've got 10 to the 23rd electrons, and you'd have to go through that calculation and see and how thick it is, what the time delay is, and getting from there to there and when these things emit radiation. So it's just a messy calculation. So you can make that kind of a prediction, and it actually does work out if you do it right. But when you're just detecting detecting light, then no. On the other hand, there are some interesting things about the energy of the light which can tell you something about the nature of the material that emitted it. We talked briefly last semester about, a hydrogen atom is going to emit photons of particular energies. Well, what I want to talk about next time is sort of trying to relate those two things together. So talk about the energy in sinusoidal waves and how these waves and how you merge this sort of wave and photon picture.
Right. Okay. Well, thank you very much. That was just something I've been thinking about since last lecture.
It was a great question, and you're right on about superposition being the issue.
Awesome. Okay. Thank you very much. I'll see you on Thursday.
Yep.
Or
kind of
Tuesday.
Just to kind of build off of what Michael said. Does that mean you theoretically could, if you could create an electromagnetic field of like the same frequency but opposite orientation, like negative amplitude, I guess, where troughs and peaks meet up, could you theoretically just make it be dark there?
That's what I mean. That's what the model says, right? So suppose you hold up a piece of black cardboard in front of the light, okay, and no light gets through, so you get a shadow in the back, right? That's what our model says is this model says is happening, is that what's happening is that all the electrons in this material are accelerated in such a way that when they re-radiate, when you add up all the waves coming from all these 10 to the 23rd electrons in this thing, they end up being exactly opposed to the we'd say out of phase. Okay, so there's a peak where there's a trough. The re-radiated radiation has a peak where the incident radiation had a trough, and so they add up to zero. And so that's what the model says. That's how you get things that are opaque.
Well, now I'm just wondering if we can make a flashlight that like projects shadows or something by like projecting an electric field that cancels out the light. That'd be kind of cool.
Be pretty cool.
So that's I actually think that's part of the stealth cloaking technology that people are working on, that somehow you're combining, you instead of the re-radiation you get from your airplane or your car or whatever, what you project out of it is radiation similar to what you'd see on the other side. So you create radiation that damps that out and then projects what you see on the other side. So I think that's you're basically kind of getting at the whole stealth technology thing.
Yeah.
Well, that's just awesome.
Yeah, it's cool, isn't it?
All right. Well, thank you.
Yeah, thank you very much.
Sure.